told us the universe is everything there is. But what if it's not? What if everything we've ever known, stars, galaxies, space, time, is just one small part of something far bigger? What if there are other realities, invisible to us, existing right beside our own? Not in a distant galaxy or far-off corner of space, but here, now, layered on top of this one. And what if we've already brushed up against them, without even realizing it? The most powerful scientific machine on Earth, the Large Hadron Collider at CERN, was built to unlock the secrets of matter. But some scientists believe it might be doing something far more radical. Beyond smashing particles, beyond studying the Higgs boson, the LHC could be revealing cracks in the very structure of reality. Some theories suggest that the LHC has the potential to produce miniature black holes, trigger events that momentarily open gateways to extra dimensions, or even leave behind traces of other universes. It sounds like science fiction, but it's based on real physics, backed by the minds of Nobel Prize-winning scientists. So here's the question: is the LHC just a particle accelerator, or is it our first real glimpse into a multiverse? In this video, we're not just exploring theories, we're asking the biggest questions science can ask, and the answers might change everything we think we know about the universe and ourselves. In 2012, deep beneath the border of Switzerland and France, something happened that turned the world of physics upside down. After decades of searching, scientists at CERN finally discovered the Higgs boson, a particle so important that some people nicknamed it the God particle. It was the missing piece of the puzzle, the one that helped explain how particles get their mass. And just like that, a major chapter of physics was confirmed. The Standard Model, the framework scientists use to describe the building blocks of the universe, got one of its biggest validations. But that discovery wasn't the end of the story, not even close. If anything, it was just the start of something even bigger, something that might change how we think about everything: reality, time, space, even the idea of existence itself. Because here's the thing: while the Higgs boson helped explain something huge, it also raised new questions. These are questions that the Standard Model doesn't answer. Questions about things we know are out there, like dark matter and dark energy, but still can't explain. And the more scientists looked, the clearer it became that what we think we know might only be a small slice of something much larger. Now, some physicists are starting to believe that our universe isn't the whole story, that it might be just one of many, one bubble in an ocean of universes, each with its own rules, its own physics, and maybe even its version of reality. It sounds like science fiction, but it's not. This idea, known as the multiverse, is being taken seriously by some of the brightest minds in the world, and the place where they're hoping to find evidence for it, it's not in some distant galaxy or on a faraway planet. It's at CERN, right here on Earth. The Large Hadron Collider, the most powerful particle accelerator ever built, isn't just a tool for studying small things. It's a window into the most extreme conditions imaginable. By smashing particles together at near light speed, the LHC can recreate moments that haven't existed since the beginning of time. It's like looking backwards into the birth of the universe. But it might also be doing something more. Some scientists believe the LHC could reveal hidden dimensions, unknown particles, or even signs that we're not alone in the cosmic landscape. Not alone, as in aliens, but not alone, as in our universe isn't the only one. So this isn't just about physics anymore. It's about figuring out what kind of reality we're actually living in. Is there more than one universe? Are there infinite versions of us living out different lives, making different choices, in worlds just out of reach? We don't have the answers yet, but if we ever do, the journey might start here. And it all begins with what the Large Hadron Collider is really doing behind the scenes. The limits of known physics. Let's be honest. Most of us were taught that physics had it all figured out. Atoms, gravity, electricity, light. All of it explained in neat little diagrams and formulas. You get particles, you get forces, and together they make up everything in the universe. Sounds pretty complete, right? But here's the truth. That version of physics? It's more like a rough draft than a finished book. The deeper scientists look into the fabric of reality, the more they realize that what we think we understand is just a sliver of what's actually out there. Take the Standard Model. It's the most successful theory in particle physics so far. It describes the known fundamental particles, like electrons and quarks, and the forces that control how they behave. It's the reason we can build computers, launch rockets, and understand nuclear reactions. But for all its success, the Standard Model has some massive holes in it. Let's start with one of the biggest ones: dark matter. Everywhere we look in space, galaxies are spinning way too fast. Based on the gravity from the visible stars and gas, they should be flying apart, but they're not. Something unseen, something we've never directly detected, is holding them together. Scientists call this dark matter, and according to the math, it makes up about 27% of the universe. That's almost a third of everything, and yet we have no clue what it actually is. The Standard Model doesn't include it. Then there's dark energy, an even stranger mystery. This one's responsible for pushing the universe apart, faster and faster, like it's being stretched from the inside. It makes up nearly 70% of everything, and yet, again, the Standard Model has nothing to say about it. Add that to the dark matter mystery, and you're looking at a universe where over 95% of its content is completely unexplained by the best theory we've got. It gets worse. Gravity, the one force we're all familiar with, the one that keeps us grounded, isn't even included in the Standard Model. The other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, are all in there. But gravity, not part of the package. That's like building a model of a car and leaving out the engine. The reason for this gap is that gravity is described by a totally different theory, Einstein's general relativity. And general relativity doesn't play well with quantum mechanics, the framework the Standard Model is built. They're like two geniuses who can't stand to be in the same room. So, we're in this weird spot. We have these two incredible theories, one that works amazingly well for tiny particles, and another that explains the motion of planets and galaxies, but they don't fit together, and when we try to merge them into one unified theory of everything, the math just breaks. It's like trying to solve a puzzle where half the pieces don't even belong to the same picture. And here's where things start to feel really shaky. The Standard Model relies on a bunch of parameters, basically numbers that describe how strong forces are, how much mass particles have, and so on. But there's no explanation for why those numbers are what they are. We just measure them and plug them in. If even one of those values were slightly different, the universe as we know it wouldn't exist. Atoms wouldn't form, stars wouldn't burn, life wouldn't happen. So the question becomes, why this universe? Why these specific rules? And why does anything exist at all? This is the wall physics has hit. We can describe the visible parts of the universe really well, but we have no idea what's underneath it. No idea why the rules are the way they are. No idea what's hiding in the dark corners of space. And no way to connect the forces that seem to shape our reality. That's why the Large Hadron Collider matters so much. It's not just some underground tunnel with magnets and wires. It's the only machine on Earth powerful enough to recreate the energy levels that existed right after the Big Bang. And that gives scientists a chance to peel back the layers of reality and look for the things the Standard Model misses. Because if we want to understand the universe, not just describe it, but really understand it, we need more than what our textbooks gave us. We need to go deeper. We need to smash protons together at nearly the speed of light and see what flies out. The LHC is our shot at breaking through that wall, and maybe, just maybe, what we find on the other side will change everything we thought we knew. What the LHC actually does: imagine a colossal underground ring, 27 kilometers long, looping beneath the peaceful countryside on the border between Switzerland and France. Now picture something happening inside that ring that sounds more like science fiction than real science. Inside this massive circular tunnel, beams of particles, specifically protons, are being hurled around at nearly the speed of light. Not just fast, we're talking 99.9999991% the speed of light. These tiny building blocks of matter are racing through a vacuum so empty it's more barren than deep space, kept on course by magnets colder than the void between galaxies. That's not exaggeration, that's fact. This enormous machine is called the Large Hadron Collider, or LHC for short. It's the biggest and most powerful particle accelerator ever built by humans. And while that might sound impressive on its own, what it actually does is even more incredible. The LHC is basically a window into the early universe, a time machine that doesn't take you back in time, but instead brings the conditions of the early universe to us. Every time those particles smash into each other at unimaginable speeds, they create tiny fireballs of energy for just a fraction of a second. And in those micro moments, something wild happens. The universe rewinds. It briefly returns to the extreme state it was in a split second after the Big Bang, super hot, super dense, and full of energy. Now you might be wondering, why go to all this trouble just to smash particles together? The answer is, because we want to understand how everything came to be, how particles get their mass, why is gravity so weak, what dark matter is made of, how the universe began, and why it looks the way it does now. See, the LHC isn't just about breaking things apart, it's about discovering what lies underneath, what's hidden in the cracks of reality. When two protons collide in the LHC, the energy of the crash can transform into new particles, some that we've seen before, and others we've only ever theorized about. It's kind of like smashing two watches together, and instead of just getting springs and gears, something new appears that didn't exist before, something that might explain the mysteries of the universe. And that's exactly how the Higgs boson was discovered in 2012. For decades, scientists believed that the Higgs boson had to exist. It was the missing piece of the puzzle, the particle that gave mass to all the others. Without it, the standard model of particle physics, our best understanding of how particles and forces work, would fall apart. But nobody had ever seen it. It was just an idea. That changed with the LHC. By accelerating protons to insanely high speeds and smashing them together, scientists were finally able to recreate the conditions needed to make a Higgs boson appear, even for just a tiny instant. And when it did, it left behind a signature, a very specific pattern in the debris from the collision. Scientists sifted through mountains of data, analyzing trillions of collisions, looking for those rare signs, and eventually they found it. It was a monumental moment in physics. The discovery of the Higgs boson wasn't just a win for the standard model, it was a win for human curiosity, a win for the idea that if you build the right tool, ask the right questions, and look hard enough, the universe will give you answers. But here's the thing. The LHC wasn't built just to find the Higgs boson. That was just one stop along the way. The real journey is still happening, because while the Higgs filled in a missing piece of the puzzle, it also raised new questions. Why does the Higgs itself have mass? Why does it have the value that it does? Could there be more than one kind of Higgs boson? Could the Higgs be connected to dark matter or to forces we haven't even discovered yet? The LHC keeps running, year after year, precisely because of those questions. So how does it all work? At its core, the LHC is designed to accelerate particles, mostly protons, which are the positively charged parts of atoms, to extremely high speeds, and then crash them into each other. This is done using a series of smaller accelerators that feed into the main ring, like on-ramps to a cosmic highway. Once inside the main tunnel, the protons are guided by massive superconducting magnets. These magnets have to be kept incredibly cold, colder than outer space, because that's the only way they can carry enough current to control the particles without overheating. These magnets steer and focus the beams, keeping them on a tight circular path for up to 11 hours before collision. Inside the LHC, two beams of protons are sent in opposite directions, circling the ring at near light speed. At specific points along the tunnel, they are directed to cross paths and collide. These collision points are surrounded by massive detectors, huge, multi-story instruments with layers upon layers of sensors. Think of them like incredibly high-tech cameras that can see subatomic particles. When the protons collide, the energy of the crash is so intense that it briefly turns into mass, creating particles that didn't exist before. Most of these particles decay in an instant, but their decay patterns are captured by the detectors. That data is then sent to computing centers, where it's analyzed for signs of new physics. And this is where things get really exciting, because every once in a while, amid all the normal, expected results, something strange shows up. A tiny anomaly, an energy imbalance, a particle that doesn't behave the way it should. And that's where discovery begins. These strange signals could be signs of new forces or unknown particles. They could even be signs that the fabric of reality isn't as simple as we think. For example, if some of the energy from a collision goes missing, disappears without explanation, it might mean a particle has traveled into another dimension. Or maybe a new kind of matter has been created, one we can't detect yet, like dark matter. It's not science fiction. These are real possibilities that physicists take seriously. The LHC is the only place on Earth that can test these ideas. But even with all this, it's not just about smashing things together randomly and hoping something cool happens. The experiments are carefully planned. Researchers design collision events to test specific theories. They change the types of particles used. Sometimes they use heavier ions like lead to create even hotter, denser conditions. Every run of the LHC is like a new chapter in an ongoing experiment, pushing deeper into the unknown. And as the technology improves, so does the sensitivity of the detectors and the amount of data they can collect. That's why CERN is upgrading the LHC into what's called the High Luminosity LHC. This new version will produce way more collisions per second, increasing the chances of catching those ultra-rare events that might hold the secrets of dark matter, extra dimensions, or new physics altogether. So, when we talk about the LHC, we're not just talking about a machine. We're talking about a window into the universe, a tool that allows us to look beneath the surface of everything we thought we knew, a device that takes us right to the edge of human understanding. It's not perfect. It doesn't give answers overnight, but it's already changed the way we see the universe, and it might still change everything again. Because every time those protons collide, we're not just looking for particles, we're looking for the truth, the search for dark matter and extra dimensions. The search for dark matter and extra dimensions stands as one of the most fascinating and perplexing endeavors in modern physics. Dark matter is something that we know exists, though we can't see it directly. Its presence is revealed through the way galaxies behave. For example, the way galaxies spin too fast, and yet the visible matter alone isn't enough to explain this speed. There's something else, an unseen force, that is exerting a pull on the galaxies, a gravitational influence that we can't directly observe but are absolutely certain exists. This invisible force is what we call dark matter. While dark matter remains a mystery, one thing is clear. It's crucial to the workings of the universe. Without it, the galaxies as we know them wouldn't behave the way they do. The evidence for its existence is undeniable, but what it actually is remains one of the greatest unsolved puzzles in science. The key to understanding dark matter might lie in the discovery of new, as yet undiscovered particles. The prevailing theory suggests that dark matter is made up of particles that don't interact with light. This lack of interaction with light is why we can't see them directly with telescopes or other instruments that detect electromagnetic radiation. However, these particles do have mass, and where there's mass, there's gravity. That means dark matter exerts an invisible gravitational force on the matter we can see, making it detectable not through direct sight, but through its influence on the universe's structure. Now, the question arises, How do we go about finding these elusive dark matter particles? How do we detect something that we can't see, touch, or even directly interact with? This is where the power of large particle accelerators, such as the Large Hadron Collider, LHC, comes into play. The LHC is at the forefront of modern physics and plays a critical role in the search for dark matter. The LHC's primary mission is to smash protons together at incredibly high speeds, recreating conditions similar to those just after the Big Bang. These high-energy collisions can, in theory, produce a whole host of new particles, some of which might be dark matter candidates. But here's the catch. Dark matter particles don't interact with light, so they won't show up on our detectors. They might, however, have a distinct signature. If dark matter particles are created in these collisions, they would escape the detectors, leaving behind missing energy, energy that disappears without any explanation. This missing energy is one of the key ways scientists hope to identify dark matter. At first glance, it might seem like a subtle clue, energy vanishing without a trace. But that missing energy could be the fingerprint of dark matter particles, slipping past our detection methods as though they were ghosts, moving through our universe without leaving a trace. It's a delicate game of deduction. Physicists at the LHC are not directly seeing dark matter, but they are looking for its indirect effects: missing energy, the absence of particles that should be there, the trace evidence of something we can't yet fully explain. But the search for dark matter doesn't end with the LHC's ability to detect missing energy. The story becomes even more fascinating when we consider the implications of some of the bolder theories in physics. One such theory is string theory, which suggests that there could be extra dimensions lurking just beyond our perception. These dimensions would be hidden from our senses, folded up in ways that we can't directly observe. Yet string theory proposes these dimensions might interact with our universe in ways that we cannot yet fully grasp. If these extra dimensions exist, they could potentially provide the missing link to understanding dark matter. Imagine for a moment that these extra dimensions are real, and that they are not just theoretical constructs, but actual parts of the universe that are simply hidden from view. What if the LHC could reveal these dimensions? That's where things get truly strange. Some physicists theorize that, by recreating extreme conditions in the LHC, tiny black holes could be formed. Black holes so small, they could only exist for the briefest of moments. These black holes might not just be interesting in themselves, they could provide a direct connection to these hidden dimensions. When we think of black holes, we usually picture massive, invisible regions in space that trap everything around them, including light. But what if, in the case of these microscopic black holes, they didn't trap matter as we expect? What if they could open a doorway, allowing particles to vanish into a hidden dimension, never to be seen again in our own universe? Such a bizarre outcome may sound like something out of science fiction, but it's actually a possibility that physicists are seriously considering. The idea of particles disappearing into hidden dimensions might seem far-fetched, but it's a legitimate area of research. The idea that we might be able to detect these disappearing particles, or even watch them seemingly vanish into another realm, is one of the most extraordinary possibilities in modern physics. This isn't just a far-off dream. It's a real possibility that researchers are actively exploring using the LHC. The idea is that, through the study of high-energy collisions and the formation of tiny black holes, we could gather evidence for the existence of these extra dimensions. If such discoveries are made, it could fundamentally alter our understanding of the universe. We've long known that we live in a universe that operates according to certain rules, rules that govern the behavior of matter, energy, and gravity. But if these extra dimensions exist, it would mean that there's far more to reality than we ever imagined. It would be like peeling back the fabric of space and time to reveal a much richer and more complex structure beneath. The search for dark matter and extra dimensions is more than just a scientific pursuit. It's a quest to understand the very fabric of reality itself. The implications of these discoveries could reshape our understanding of physics and the cosmos. It could rewrite the textbooks and change the way we think about space, time, and the forces that govern our universe. This is why the hunt for dark matter is so crucial, not just because of what we might find, but because of what it could teach us about the true nature of the universe. In many ways, the search for dark matter and extra dimensions is also a search for something deeper, a search for the unknown. It's a quest driven by curiosity, by the desire to uncover the secrets of the cosmos. The LHC, with its immense power and precision, is at the forefront of this quest. Every collision, every experiment, brings us one step closer to the truth. And while we may not have all the answers yet, the search itself is a journey that continues to inspire and excite scientists and lay people alike. At the end of the day, the hunt for dark matter and extra dimensions is as much about the process of discovery as it is about the answers. It's about pushing the boundaries of what we know, challenging the limits of our understanding, and expanding our view of the universe. The search is ongoing, and while it may take time before we uncover the full story, the promise of a groundbreaking discovery remains a constant driving force in the world of physics. So, as the Large Hadron Collider continues its experiments, scientists remain hopeful. Every collision could bring new insights into the nature of dark matter, extra dimensions, or other hidden phenomena in the universe. The answers may be just around the corner, or perhaps they'll take decades to reveal themselves. But one thing is certain: the journey to understand the unseen forces of the universe is one of the most thrilling scientific endeavors of our time. Could the LHC detect the multiverse? The Large Hadron Collider, LHC, the world's most powerful particle accelerator, has long been a beacon for answering the deepest questions of physics. But could it also help answer one of the most mind-boggling questions of all? Is our universe just one of many in a vast multiverse? To understand why this question is even being asked, we have to dive into the theory of inflation. Not the kind of inflation you might think of when it comes to the economy, but rather a cosmic inflation that occurred shortly after the Big Bang. This theory suggests that the universe expanded at an extraordinary rate, much faster than the speed of light, within the first moments of its existence. It was a time when space itself stretched out, creating the vast, uniform cosmos we see today. What's even more fascinating is the idea that this rapid expansion might not have stopped. In fact, some scientists propose that the universe could still be expanding, but instead of continuing as one, it split into numerous bubbles. Each of these bubbles would eventually evolve into its own separate universe, with its own set of physical laws and properties. Now, let's circle back to the LHC. At first glance, the connection between a particle collider and the multiverse might seem a bit far-fetched. After all, how can smashing tiny particles together in a lab possibly reveal the existence of other universes? But it's not as far-fetched as it seems. The theories surrounding the multiverse suggest that there might be subtle clues, tiny, almost imperceptible fingerprints, left behind in the behavior of particles. These could show up in high-energy collisions, like the ones produced at the LHC. Imagine for a moment that the LHC is capable of reaching energies so high that they could, in theory, cause particles to behave in ways we've never seen before. Under normal conditions, particles behave according to the laws of physics as we know them. But in certain extreme environments, like those created by the LHC, something strange might occur. Particles could decay in unexpected ways, or they could suddenly lose energy without explanation. In these moments of oddity, some physicists believe that we might be catching glimpses of interactions with other universes. The idea is that, if multiple universes do exist, they might somehow interact with our own in ways that leave tiny marks in the particle data we measure. These marks wouldn't be obvious at first, but with the right kind of detection, they could provide the first solid evidence that we live in a multiverse. But there's more. Another intriguing possibility is that the LHC could help us detect extra dimensions. dimensions beyond the familiar four of space and time that we experience in our everyday lives. According to theories like string theory, there may be additional dimensions hidden from our view, ones we can't directly perceive. But if these dimensions exist, they could have a profound impact on the way particles behave. In fact, some scientists believe that the LHC could create tiny black holes by tapping into these extra dimensions. Now, before you get concerned about the end of the world, rest assured that these black holes wouldn't pose any danger. They would be incredibly small, so small in fact that they would evaporate almost instantly. However, their brief existence could offer a tantalizing hint that space-time is not as limited as we once thought. In this context, the creation of these minuscule black holes might not just be an exciting find in and of itself. It could actually be the key to proving that our universe is just one bubble in an endless sea of bubbles. If the LHC were to detect such black holes, or observe anomalies in particle behavior that suggest extra dimensions, it would open up an entirely new avenue of exploration. Not only would we have evidence that other dimensions exist, but we'd also be forced to reconsider the very nature of reality. The multiverse, once considered little more than a speculative idea, might no longer be just a far-off dream of science fiction. It could become a legitimate area of scientific inquiry. Of course, this doesn't mean the multiverse is a certainty, nor does it mean we'll uncover definitive proof of its existence through the LHC. The universe is a vast and mysterious place, and the questions we ask are often more complicated than we can currently comprehend. The LHC's experiments are still unfolding, and while it has already made monumental discoveries, such as confirming the existence of the Higgs boson, it may take years, or even decades, before we start to see signs that point toward the multiverse. However, the LHC represents one of our best chances to explore the very fabric of reality. Its ability to probe particle behavior at the most fundamental level could, one day, help us answer questions that have tantalized physicists for centuries. If the multiverse is real, the fingerprints of those other universes might just be hiding in the data, waiting for the right set of experiments to bring them into the light. So, can the LHC detect the multiverse? The answer, for now, is that we don't know for sure. But as the LHC continues to push the boundaries of what we can observe in the subatomic world, it might just lead us to the most extraordinary discovery in the history of science. And if we do find evidence of the multiverse, it would not only transform our understanding of the cosmos, but might also reveal a deeper, more interconnected universe than we ever imagined. Why the Higgs boson still matters. The Higgs boson. It's a name that's become almost synonymous with cutting-edge physics in recent years. For the average person, it might seem like a subject that gets talked about ad nauseum in scientific circles. In fact, there's often a sense that the Higgs boson has been discussed so much that we should already have all the answers. After all, it was discovered back in 2012, with one of the biggest scientific discoveries in history made at the Large Hadron Collider, LHC. So why nearly a decade later does the Higgs still dominate conversations about the foundations of the universe? Here's the thing. The reason the Higgs is still a topic of discussion isn't because we're obsessed with it, but because we don't fully understand it yet. Despite the excitement surrounding its discovery, the Higgs boson holds many secrets. We know more than we ever did before, but there's still so much we're missing. The Higgs might seem like an old story, but in reality, it's just the beginning of a much larger narrative that could radically reshape our understanding of the cosmos. At its core, the Higgs boson is tied to something profoundly important: the Higgs field. This field is a key component in explaining why particles have mass in the first place. Without it, the universe as we know it wouldn't exist, at least not in a form we'd recognize. But even though the Higgs boson helped confirm the existence of this field, we still don't understand everything about it. In fact, some of the most fundamental questions surrounding the Higgs remain unanswered. Why does the Higgs field even exist? Why does it have the mass it does? And perhaps most intriguingly, how does it interact with some of the universe's most elusive components, like dark matter and gravity? These aren't just idle questions. They're the very ones that could unlock the next frontier of physics. If the Higgs behaves in unexpected ways, it could open a door to realms of science that are completely unknown to us. Imagine what it would mean if the Higgs were found to be more than just a particle. What if it were the key to understanding some of the most puzzling phenomena in the universe, such as dark matter or the force of gravity itself? It's a tantalizing thought, and one that many physicists are now exploring in detail. The idea that the Higgs might be hiding something even bigger than itself has gained traction in recent years. The Higgs boson could be the portal to new physics, possibly even leading to a revolution in our understanding of the fundamental laws of nature. Scientists working at the LHC aren't just measuring the Higgs for the sake of curiosity. They're doing it with a specific purpose in mind. They're searching for any sign that the Higgs might behave differently than what we've predicted. When scientists first discovered the Higgs boson, they did so with a model of the universe in mind, a model called the Standard Model. The Standard Model has been the backbone of particle physics for decades, explaining everything from how atoms are structured to the fundamental forces that govern the universe. But while it's been incredibly successful, it's also incomplete. There are still huge gaps in our knowledge, and the discovery of the Higgs doesn't fill those gaps. It actually highlights them. The Higgs boson itself is a perfect example. In the Standard Model, the Higgs is meant to be a simple, predictable particle. It interacts with other particles in very specific ways, and scientists have a pretty good idea of how it should behave. But what if it doesn't behave exactly as we expect? What if the Higgs shows signs of something new? If this happens, it could throw everything we think we know about particle physics into question and lead to an entirely new framework for understanding the universe. It's this very possibility that keeps scientists at the LHC coming back to the Higgs year after year. They're not just looking for confirmation of what we already know. They're hoping to uncover something more. The potential for a discovery that could upend the Standard Model is one of the biggest motivators behind the ongoing experiments at the LHC. Now, some may wonder, why does it matter if the Higgs behaves differently than expected? Well, consider this. The behavior of the Higgs is tied to some of the most fundamental questions in physics. For example, the way it interacts with other particles could help us understand the nature of dark matter. Dark matter makes up a significant portion of the mass of the universe, but we've never been able to detect it directly. If the Higgs interacts with dark matter in unexpected ways, it could be the first clue we've had in decades about what dark matter really is. The Higgs could also provide insights into gravity, another mysterious force that scientists are still struggling to fully understand. Gravity is the force that holds the universe together, yet it doesn't fit neatly into the framework of the Standard Model. If the Higgs is tied to gravity in ways we don't yet comprehend, it could be the key to developing a theory of quantum gravity, a theory that combines quantum mechanics and general relativity, two of the most successful theories in physics that, as of now, don't quite fit together. In fact, there are some physicists who believe that the Higgs could help us uncover a much bigger mystery, the possibility of a multiverse. The idea of a multiverse, that our universe is just one of many, is a radical hypothesis, and one that's difficult to test. But if the Higgs behaves in a way that we don't expect, it could provide a crack in the door through which we might glimpse other universes. It sounds like science fiction, but it's exactly this kind of thinking that has driven breakthroughs in physics for centuries. Of course, the idea that the Higgs might be connected to a multiverse is speculative at best, but that's part of the excitement. The Higgs boson is not just a particle in a lab experiment. It's a potential bridge to a new understanding of the cosmos. It's a puzzle piece that could fit into a much larger picture, one that could forever change the way we think about the universe and our place in it. That's why the Higgs boson still matters. It's not just about confirming a long-standing theory. It's about exploring the unknown, asking questions that have no easy answers, and searching for clues that might lead us to discoveries that are beyond our current comprehension. In many ways, the Higgs is the key that could unlock the next chapter of physics, and maybe even rewrite the laws of the universe itself. So even though the Higgs has been talked about a lot, it's still very much a mystery. And that's what makes it so important. Because in the world of science, it's the mysteries that drive us forward. And the Higgs, for all the attention it's gotten, is still one of the biggest mysteries of them all. The matter-antimatter problem. There's a profound and baffling mystery at the heart of our universe, one that has stumped scientists for decades. If we were to rewind time to the moment of the Big Bang, the birth of everything we know, there was an expectation that it would have created equal amounts of matter and antimatter. At first glance, this might seem simple enough to understand. We know that matter is everything around us, stars, planets, people, and even the air we breathe. But antimatter? Well, that's the tricky part. Antimatter is essentially the opposite of matter. Every particle has a corresponding antimatter counterpart. For instance, the electron, the particle that makes up atoms, has an antimatter twin called the positron. Instead of a negative charge, the positron carries a positive one. It's the mirror image, with opposite properties, but equal in magnitude. You might think of it as the antithesis of the building blocks that make up the world we know. In theory, when matter and antimatter meet, they should annihilate each other in a burst of energy. They cancel each other out in a perfectly balanced exchange. If the Big Bang had produced equal amounts of both, they should have destroyed each other completely in this annihilation, leaving behind nothing but pure energy. But that's not what happened. Instead, the universe seems to be made almost entirely of matter. The antimatter is nowhere to be found. So, where did all the antimatter go? This is one of the deepest and most perplexing questions in physics. The very fact that the universe exists at all suggests that something happened early on to tip the balance between matter and antimatter in favor of matter. Without that imbalance, the universe would have simply canceled itself out, and everything, galaxies, stars, planets, even us, wouldn't have come into existence. But this imbalance, however it happened, is still largely a mystery, and scientists, using the most advanced tools at their disposal, are on a quest to find the answers. To understand the scope of the problem, it's helpful to take a step back and think about the Big Bang. When the universe began, it wasn't the vast, complex cosmos we know today. Instead, it was a hot, dense soup of particles: protons, neutrons, electrons, and their counterparts, the antiparticles. In this early phase, matter and antimatter existed in roughly equal amounts. But as the universe cooled and expanded, the particles began to combine, forming atoms. This is when things started to take a strange turn. Instead of the expected annihilation of matter and antimatter, what we observe today is a universe made almost entirely of matter, with very little antimatter in sight. For a long time, physicists have been searching for an explanation, but finding one has proven to be a monumental challenge. This imbalance, this asymmetry, is known in the scientific community as the matter-antimatter asymmetry problem. It's a puzzle that sits at the intersection of cosmology, particle physics, and fundamental theory. It asks, why is the universe made of one and not the other? And even more perplexing, how did that imbalance come to be? As we dig deeper into the world of subatomic particles, we begin to see that the answer might lie in something subtle. Perhaps there's a tiny difference between matter and antimatter that existed from the very beginning, something so small that we didn't notice it at first. It's a tiny imbalance, but it had huge consequences. It's this very tiny difference that could explain why matter survived and antimatter vanished. This brings us to one of the most powerful tools in modern physics, the Large Hadron Collider, LHC. Located at CERN in Switzerland, the LHC is the world's most advanced particle accelerator, capable of smashing particles together at nearly the speed of light. This allows scientists to explore the fundamental building blocks of the universe. One of the LHC's most ambitious goals is to study super-rare particle decays, looking for any sign of an asymmetry between matter and antimatter. These experiments are not only mind-bending in their complexity, but they hold the key to unlocking a potential answer to one of the greatest mysteries in all of science. Scientists at the LHC are investigating whether there's a tiny, subtle difference in the way that matter and antimatter behave. If they can detect even the smallest of discrepancies in these particle decays, it could provide the breakthrough they've been looking for. Just a slight imbalance, one that might be undetectable to the naked eye, could explain why the universe is made of matter instead of being a completely empty, energy-filled void. But why are these particle decays so crucial? Well, in particle physics, the laws that govern particles and their interactions are well understood. We know that particles like protons and neutrons, matter's building blocks, are formed through a delicate balance of forces. But antimatter particles, which are the mirror image of these particles, are not as straightforward. For example, in certain conditions, the way they decay could differ from matter in tiny, almost imperceptible ways. These differences are known as CP violation, charge parity violation. If CP violation occurs to a greater extent than we currently understand, it might explain why antimatter didn't stick around and why matter ended up dominating the universe. So far, however, there's been no definitive evidence that CP violation could explain the matter-antimatter imbalance. But physicists haven't given up. They're using the LHC's particle collisions to push the boundaries of what we know about the fundamental forces of nature. They are examining rare processes that might show us this elusive difference, searching for that elusive signal that could finally unravel the mystery. At the heart of this search is a tantalizing possibility. If scientists find even a small imbalance in how matter and antimatter behave, it could rewrite our understanding of the universe. It could explain the very origins of everything around us, from the stars that light up the night sky to the atoms that make up our bodies. It could offer us a window into the forces and particles that govern the universe's birth. It could even provide clues to what's beyond the visible universe and what might lie hidden in dimensions we can't yet detect. The implications of solving the matter-antimatter problem would be staggering. It would bring us closer to understanding the Big Bang itself, offering answers to questions about the nature of space, time, and the fundamental forces that govern everything in existence. More importantly, it would help us understand why the universe is the way it is today. Without that subtle imbalance in the early universe, none of it would have been possible. But what happens if scientists don't find any evidence of this imbalance? If no tiny discrepancy turns up, we could be left with an even bigger question. Why did the universe fail to annihilate itself? Was there some unknown process or event at the dawn of time that caused matter to dominate? Or is there something we don't yet understand about the nature of antimatter and its behavior? For now, the mystery remains unsolved. But the search continues. And with every experiment, every particle collision, and every discovery made at the LHC, we get one step closer to understanding one of the universe's deepest, most puzzling questions. Until then, the matter-antimatter problem stands as a testament to just how much we still have to learn about the cosmos. Long-lived particles and the hidden sector. One of the most intriguing and mysterious concepts in modern physics is the idea of long-lived particles. These particles don't behave like the familiar ones we've come to know from the standard model of particle physics. Instead, they hang around longer than we expect, defying the usual rules of particle decay. This anomaly has captured the attention of many physicists, as it could point to something far beyond our current understanding. In the world of particle physics, most particles follow a pretty predictable cycle. They come into existence, interact with other particles, and then decay, often in a fraction of a second. This is true for everything from the tiniest quarks to the heavier particles we encounter in high-energy experiments. But imagine for a moment that you were standing in the lab, watching a particle, one that you expected to decay almost immediately, staying intact for much longer than it should. That's exactly what scientists are starting to observe with these long-lived particles. You see, the standard model has a specific set of rules for how particles interact, decay, and exist. These rules help scientists predict what will happen when they smash particles together in accelerators like the Large Hadron Collider, LHC. But sometimes, when they examine the aftermath of these collisions, they find something unexpected, particles that linger far longer than anticipated. At first glance, this might not seem like such a big deal. After all, scientists expect the unexpected in a field as wild as particle physics. But when you dig a little deeper, the idea of long-lived particles begins to raise some really fascinating possibilities. Could they be pointing to something new, something we've never seen before? Could these particles be connected to a hidden layer of reality, one that exists right alongside our own, but is completely separate from the physics we know? That's where the hidden sector comes into play. The hidden sector is a theoretical concept that suggests there may be particles, forces, and interactions that exist beyond the reach of our current understanding. These are not just particles that we've missed or haven't been able to detect yet. They are, in some sense, outside the physics we currently describe. They don't fit neatly into the standard model, and they might not even interact with the forces we've spent so much time studying, like gravity, electromagnetism, and the strong and weak nuclear forces. In this hidden sector, particles could exist that behave in ways we can't predict. They might have properties that make them resistant to decay, or able to interact in strange ways that don't match anything we know. And these long-lived particles could be the first sign that we're starting to uncover a completely new layer of the universe's underlying structure. Imagine for a second what this might mean. If the LHC, or another particle accelerator, were to discover these long-lived particles and show that they come from this hidden sector, it would be like finding an entirely new chapter in the book of physics, one that we had no idea existed. It's as if we've been reading the story of the universe with half the pages missing, and suddenly, someone hands us the rest of the manuscript. It could open up an entirely new field of research, one where scientists can begin to understand how these hidden forces and particles operate. The idea of a hidden sector is not some far-out fantasy either. There are serious theories that suggest such a sector could exist, and that it might even help solve some of the most puzzling questions in modern physics. For instance, one of the biggest mysteries in the field is dark matter. We know dark matter exists because of its gravitational effects on galaxies, but we have never been able to detect it directly. What if dark matter is made up of particles that come from this hidden sector? What if these particles don't interact with light or the other known forces the way we expect? That could explain why we can't detect them using traditional methods, and it might even explain why long-lived particles behave the way they do. In fact, some physicists suspect that the hidden sector could be responsible for a lot of the phenomena we've been struggling to understand. It could provide new insights into everything from dark energy to the forces that govern particle interactions at the most fundamental level. If we can detect particles from this hidden sector, particles that seem to live much longer than we expect, it could be the breakthrough we need to unlock the next level of understanding in physics. But discovering these long-lived particles and connecting them to the hidden sector isn't going to be easy. It's one of the most challenging areas of research in particle physics today. The problem is that these particles are, by their very nature, elusive. They don't interact with the known forces in the same way, and they don't decay like we would expect. This makes them difficult to detect directly. They might pass through detectors without leaving any trace, or they might only interact with other particles in very specific ways, making it easy for them to go unnoticed in a sea of data. That's why the work being done at the LHC is so important. The LHC is one of the most powerful tools in the world for probing the deepest secrets of the universe. It accelerates protons to near light speeds and then smashes them together, recreating conditions similar to those just after the Big Bang. These collisions produce a shower of particles, and by studying the aftermath, scientists can detect particles and forces that are otherwise hidden from view. The LHC's high-energy experiments give researchers the chance to explore not just the standard model, but also the possibility that there's more to the story, If long-lived particles do exist, they might be produced in these collisions, allowing scientists to detect their strange behavior and perhaps even uncover the hidden sector. Of course, this would require a lot of precision, careful analysis, and an understanding of the intricate details of particle physics. But if scientists can find a way to detect these long-lived particles, it could revolutionize the field. It's not just the LHC, though. Other experiments and observatories around the world are also looking for signs of the hidden sector and long-lived particles. In some cases, scientists are developing new detectors that are more sensitive to these elusive particles. In other cases, they're looking for indirect evidence, such as unusual patterns of particle decay or unexplained phenomena that could point to the existence of particles from this hidden world. The search is on, and while we may not have definitive answers yet, every new piece of data brings us closer to understanding this strange and fascinating possibility. If long-lived particles really do exist, they could change everything we know about the universe. They could reveal new forces, new interactions, and perhaps even new dimensions of reality that have been hidden from view for all of human history. But even as we wait for the evidence to come in, the idea of the hidden sector forces us to rethink everything we thought we knew about the universe. It suggests that the world we see, the world of atoms, light, and familiar forces, might only be the tip of the iceberg. Beneath the surface, there could be entire realms of physics that we have yet to explore. And within these realms, long-lived particles might be waiting for us to discover them, offering the key to unlocking the next great chapter in the story of the cosmos. In the end, the search for long-lived particles and the hidden sector is more than just a quest for new knowledge. It's a journey into the unknown, a challenge to the very foundations of physics, and a reminder that the universe is far more mysterious and complex than we can imagine. And with every experiment, every discovery, we take one step closer to understanding the hidden layers of reality that may be just beyond our reach. Supersymmetry and what's next. One of the most amazing ideas scientists are chasing right now is supersymmetry, or SUSY for short. Imagine a universe where every known particle, from the tiniest quarks to the elusive neutrinos, has a heavier, mysterious partner particle we haven't discovered yet. It's like a cosmic shadow world, hidden just out of reach, but influencing everything we know about physics. So, what could these partner particles mean for us? Let's take a closer look. Supersymmetry might help solve some of the most persistent mysteries in physics. For one, it could explain why the Higgs boson, the particle responsible for giving mass to other particles, is so surprisingly light. After all, the Higgs should weigh much more than it does, but supersymmetry could provide a reason for this strange behavior. And what about the Big Bang? Supersymmetry might help explain why the universe didn't simply collapse upon itself after the initial explosion. If the particles we know about had no supersymmetric partners, it could have led to instability in the very early universe. Instead, these hypothetical particles could have played a crucial role in maintaining the balance, preventing a cosmic disaster. Then, of course, there's dark matter. This elusive substance makes up a large portion of the universe, but we've never directly detected it. Supersymmetry steps in again with a potential solution, as it predicts the existence of dark matter particles in the form of supersymmetric partners. These particles could be the key to understanding this invisible force that shapes galaxies, yet remains completely undetectable with current methods. However, despite these fascinating possibilities, the search for supersymmetry hasn't yielded any concrete results so far. The Large Hadron Collider, LHC, the world's most powerful particle accelerator, has been at the forefront of this quest, smashing particles together in hopes of revealing these hidden partners. But up until now, the LHC hasn't found any direct evidence of supersymmetric particles. This has left some scientists wondering, are they even out there? Could they be hiding in plain sight, just beyond the reach of our current technology? That doesn't necessarily mean that supersymmetry is a dead-end theory. In fact, it could simply mean that these particles are heavier than we expected, The LHC has only been able to probe a certain range of particle masses, and it's possible that the supersymmetric particles are too massive for it to detect with the current setup. But don't worry, the search isn't over. The LHC is undergoing a massive upgrade, and soon it'll be more powerful than ever. The new high-luminosity LHC, set to go live in a few years, will dramatically increase the number of collisions the collider can produce. In fact, the number of collisions will increase by a factor of 10. More collisions mean more data, and more data means a higher chance of discovering something new. With this upgrade, scientists are hopeful that they'll finally uncover the supersymmetric particles that have been eluding us for so long. The journey doesn't end with the LHC either. There are other experiments, telescopes, and observatories working on detecting the invisible traces of supersymmetry in different ways. While the search for supersymmetric particles has so far been elusive, the future looks promising. The more data we collect, the closer we'll get to understanding the true nature of the universe. And that's where we find ourselves today, on the edge of what could be a new era in physics, with the mysteries of dark matter, the Higgs boson, and the stability of the early universe, all potentially tied to supersymmetry. The next few years could hold the key to unlocking some of the deepest secrets of the cosmos. As scientists continue their search, we're reminded that the universe has a way of keeping its secrets hidden, waiting for us to find the right tools, the right theory, and the right moment to uncover them. The high-luminosity LHC is just one of many steps we'll take toward understanding the unknown, but it could very well be the breakthrough we've been waiting for. As we look to the future, we're not just searching for new particles, we're searching for a deeper understanding of the universe itself. So, what's next? The possibilities are endless. The mysteries of supersymmetry, dark matter, and the nature of reality are all still waiting to be explored. As the search continues, one thing is certain. We're on the brink of something extraordinary, deeper and more reflective. It's almost mind-boggling to think about what might lie deep beneath our feet. In the heart of a massive circular tunnel, hidden underground, we could be standing on the precipice of the next great leap in our understanding of the universe. This tunnel, the Large Hadron Collider, isn't just a piece of advanced machinery or a complex experiment. It represents our most ambitious attempt to ask the universe its most profound questions. The answers, though, are not always what we expect. Sometimes they're even more mysterious than we could have ever imagined. When scientists first set out to explore the building blocks of matter, they had no idea what they were going to find. The discovery of the Higgs boson, for example, was a breakthrough of incredible importance. But that's only one piece of the puzzle. The collider has already shattered long-held beliefs, tested theories, and paved the way for understanding phenomena that were once considered entirely theoretical. But we are only scratching the surface. The more we learn, the more we realize how much is still left to uncover. The LHC is like a cosmic microscope, pushing the boundaries of our knowledge and challenging the limits of our imagination. Its experiments have already opened new doors to possibilities that were once relegated to the realm of science fiction. We've learned more about particle interactions, fundamental forces, and the very structure of space-time itself. But, for all its success, the universe has a way of keeping its greatest secrets hidden, just out of reach, teasing us with glimpses of what might be. With each new discovery, we begin to peel back a layer of the universe's vast, intricate design. But even as we solve one mystery, we are left with even bigger questions. The collider, with its immense power and precision, offers us the chance to probe deeper into the fabric of reality. Could there be more dimensions beyond the ones we know? Could there be other universes, lying just beyond our perception, waiting to be discovered? These questions are no longer the stuff of speculation. They are now tangible challenges for physicists. We know that reality is far stranger and more complex than we've ever imagined. And the more we learn, the more we realize that we've barely begun to scratch the surface. Supersymmetry, hidden sectors, long-lived particles, These are just a few of the fascinating theories that are emerging from the latest experiments. But each of these ideas leads to even more questions. They raise the possibility of new kinds of matter, unseen forces, and even entire dimensions that may be hidden from our view. If these theories hold any truth, they could completely rewrite everything we know about the universe. But something is humbling about the quest for knowledge. Despite all of our advancements, we are still just small players in the vast expanse of space and time. We are mere observers, trying to make sense of a universe that has existed for billions of years, long before we ever thought to ask these questions. And yet, through the work done in places like the Large Hadron Collider, we are inching closer to understanding the deeper nature of reality. The true power of the collider isn't just in the experiments it conducts or the particles it uncovers. Its real value lies in the way it challenges our assumptions and forces us to confront the mysteries of the cosmos head-on. Each collision, each experiment, offers a fresh perspective, a new way of looking at the universe. It forces us to reconsider what we thought we knew about the fundamental laws of physics, and to remain open to the possibility that there are more layers to reality than we can perceive. There's an undeniable sense of excitement that comes with this journey. We live in an age where the lines between science fiction and science fact are becoming increasingly blurred. Ideas that once seemed fantastical, like parallel universes or dimensions beyond our own, are now being tested in labs. We're not simply waiting for the universe to reveal its secrets to us. We're actively seeking them out, using the most advanced technology we've ever created. And with each experiment, each new piece of data, we are one step closer to understanding the grand design of everything. Yet there's a certain mystery that remains. Even as we unlock new chapters in the story of the universe, the ending remains elusive. What will we find next? Will it be another breakthrough that shakes the very foundations of physics? Or will it lead us to a deeper mystery, something even more profound than what we've already discovered? Whatever it is, it will undoubtedly challenge our understanding and change the course of human knowledge forever. The pursuit of knowledge is an ongoing journey, one that stretches far beyond the confines of our current understanding. The universe is vast, and our exploration of it has only just begun. The answers we've found so far are just the beginning. Every discovery opens up more questions, and every question leads us down new paths of exploration. Perhaps the most exciting part of all is that we don't yet know what lies ahead. The questions we are asking today may seem unimaginable to those who come after us, just as the questions of the past seemed strange to us. But one thing is certain: the search for answers will continue. And in that search, we may just discover the greatest mystery of all. Subscribe.